All right, today we are covering section 6.5. So we're talking about complex numbers in polar form. And I'm not totally sure, but I think we say this Demoivre's theorem. So I put just all the theorems and formulas and all of that up at the top here. For the final exam, I do not believe that any of these formulas are on the formula sheet. Now, certainly, I would strongly suggest that in that box area that you're allowed to use, that you write these formulas in that area, because there is always something from this section on the final exam. Usually it's either the complex roots or it's Demoivre's, one of these, but there's always at least one, if not two, questions from this section, usually on the final exam. So this is probably the most difficult section that we cover all year. So I would really take care when you are completing the practice problems, to try to treat them as if, they were a question on the final exam. Really seek to understand what you're doing because, like I said, there's always something from this on the final exam, if not two things. So when we have a complex number, we know that standard form of a complex number is this a plus bi format. So where a is the real part, b is the coefficient of the imaginary part. So the absolute value of a complex number, which we just use z to stand for a general complex number, the absolute value of the complex number is going to be equal to the square root of a squared plus b squared. So really almost like using the Pythagorean theorem, where you would do a squared plus b squared and then take the square root. So same idea there. When we are writing complex numbers, we sometimes write them in rectangular form and sometimes we write them in polar form. So this is the polar form of a plus bi, and that is r times the quantity cosine theta plus I sine theta. So remember that instead of using x and y like rectangular coordinates do, we use r and theta. So we've got the r here, we've got the theta here. Along with this polar form, kind of gives us some additional information that we don't always directly state in the formulas, but if we have all of this going on, it's always going to be true that r is equal to the absolute value, which means that r itself is the square root of a squared plus b squared. So same as the absolute value formula up here. We also, because sometimes we have the a and the b, so we have the rectangular form, if we want to find theta, we can use the formula tangent theta equals b over a. Because if I'm trying to solve for theta, or if I know theta, it doesn't matter which way, we can solve either way. But if I'm trying to find theta and I know a and b, I can just do inverse tangent and that gives me my values. So they're going to ask for some of your answers in rectangular form, some of them in polar form, so you just have to be really careful. I'm not going to read the next two formulas for product and quotient. I think they're pretty self-explanatory how we plug in because our first complex number has its r1, theta 1, and then the second one has r2, theta 2. Demoivre's theorem is when we are taking a power of a complex number. So remember, z is just what we use for a general complex number. If I'm raising it to the n power, that is the same as this because this is the polar form of the complex number, so still raised to the n. And they are telling us that the way that we would take that power is to apply that power to the r part, and then the n actually goes on to the theta as a product. So here you can see sometimes it gets lost in there, but it's sine n theta. It's hard to see sometimes since we've got two n's in a row there. Last formulas for complex roots of a complex number, and this one we'll get to, we'll do an example, but it'll sometimes ask you to find all the complex roots. So n is just the nth roots that we're talking about. So if we're talking about finding the sixth roots of a complex number, then that would mean that n would be 6. So we would do sixth root of r, and then you can see that here we start plugging in 0 for k for the first root, then we plug in 1, then we plug in 2, all the way up to n minus 1. So what this means for us is that let's say that n equals 6, like the example that I just gave. If we're finding the complex sixth roots, that means that we're going to have k equals 0, 1, 2, 3, 4, and 5, because you always stop one less than the roots you're trying to find. All right, so that's our formulas, and I would very strongly suggest that you hold on to this, don't lose this. A lot of these formulas you really are going to need to put in your box for the final exam. So let's take a look at the examples now. Example 1, plot -3 minus I, find its absolute value, and write it in polar form. So we've got 3 different tasks here. First, plot it. So we've done plotting of complex numbers before. So remember that when we are plotting complex numbers, the real axis is here, the imaginary axis is here. So -3 minus I means that I'm going to go left 3 and down 1, and so this would be my plot. Find its absolute value. So the absolute value of -3 minus I, that's going to be our first formula. So we're going to do the square root of a squared, and a is -3, so -3 squared plus b squared. Remember, b is what's in front of the I. It doesn't include the I. So that would be plus -1 squared. So that gives us the square root of 9 plus 1, which is square root of 10. And square root of 10 does not simplify, so that means that this is my absolute value. And then my final task is to write it in polar form. So in polar form, I need my r and I need theta. So in this case, I'm going to have to use this formula over here to find my theta. So I know that tangent of theta equals b over a. So b is -1 and a is -3. So I'm going to do inverse tangent of 1/3 equals my theta. It's really important that you pay attention to what mode you're in here. Here I'm going to want my answer in degrees because it doesn't specify, so degrees is obviously easier. I know that that's not a unit circle value, the 1/3 isn't, so I'm going to do inverse tangent of 1/3, and that gives me about 18.4 degrees. So theta is 18.4 degrees. And so now I have my r, because r, remember, is the same as the absolute value, and I have my theta, so I can write it in its polar form. So polar form, z equals r, which is radical 10, times cosine of 18.4 degrees plus I times the sine of 18.4 degrees. And then that is the last thing that we needed to do for that example. Example 2. This one, we want to write it in rectangular form. So this one is a lot easier to go from polar form to rectangular form. We really just need to evaluate. So 4 pi over 3, that is a unit circle value. So it's right over here in quadrant 3. And in quadrant 3, the reference angle there is 60 degrees, or pi over 3. So at 60 degrees, I know my cosine is generally the 1/2 value. The sine is the radical 3 over 2. So because I'm in quadrant 3, both of those values are going to be negative. So this is the ordered pair on the unit circle where I land, which means that I'm doing 6 times cosine of 4 pi over 3 would be negative 1/2 plus I times the sine of 4 pi over 3, which is negative radical 3 over 2. And then I'm just going to distribute. So 6 times negative 1/2 gives me negative 3. I know I'm going to have the I with my answer. The 6, when I multiply times the 2, those are going to cancel each other out. So I end up with minus 3I radical 3. Generally, the rule is that we put i's after whole numbers before radicals. So I would probably write it like this. Because of the standard form thing, I would also accept minus 3 radical 3i with the I at the end. So either way. All right, example 3, find the product of the complex numbers, leave the answer in polar form. So my original is in rectangular form, so that presents a problem if I want polar form. And notice that the formula is in polar form. So first thing I need to do is actually convert each of these complex numbers to polar form. So on z sub 1, if I want to find its r, so r sub 1, I'm going to have to do the a squared plus b squared there. A is 1, so 1 squared plus coefficient of the I is also 1, so that gives me square root of 2. So that's the radius for my first complex number. Then I'm going to need to find the theta, so tangent of theta equals 1 over 1, which is 1. So inverse tangent of 1. This is a unit circle value, unlike what we had in example 1. There's no unit circle value that has a tangent of 1/3, so that's why we used degree mode and did it that way. When it is a unit circle value, you need to use radians, and they need to be exact answers. So tangent becomes 1 when sine divided by cosine is 1, which means the sine and cosine are the same. Now there are 2 places where the sine and cosine are the same. That happens in both quadrant 1 and quadrant 3. So in quadrant 1 at the 45-degree angle at pi over 4, we have radical 2 over 2 and radical 2 over 2. In quadrant 3, they're both negative. So it's important that you know which one to use. You know which one to use by looking at the original complex number. Z1 is going to be in quadrant 1, which means we're going to use the quadrant 1 answer. So we're going to use pi over 4 here. So this is our theta 1. Now we do the same for our Z2. So R2 is going to be the square root of radical 3 squared plus negative 1 squared. And so radical 3, when I square it, just gives me 3. This gives me 1. So then I have 3 plus 1, which is 4. Square root of 4 is 2. So in this case, radius 2 is just 2. Tangent of theta is going to be equal to negative 1 over radical 3, which again is also a unit circle value. So it's important that we figure out what quadrant we're in. And in this case, I have radical 3, which is positive for my A, and negative 1, which is negative for my B. So Z2 is going to be in quadrant 4. So what I need to look at is whether I know that this isn't a 45-degree angle. I know it's not a quadrantal, so I know this is either the 30-degree reference angle or the 60. So if you're not sure, you can kind of divide to figure it out. So it's tangent is sine divided by cosine. If I do radical 3 over 2 divided by 1/2, that gives me the radical 3 in the numerator. So I know it's going to be the 1/2 divided by the radical 3 over 2, which means sine value is 1/2. Cosine value is radical 3 over 2. So that happens at 30-degree reference angles if you look on your unit circle. So I want in quadrant 4 the 30-degree reference angle, and I always want it in radians. So that's going to be 11 pi over 6. So that's going to be my theta 2. All this work, and I haven't even used the formula yet. So luckily, not all of them are quite this complicated, but you can see why I said it really is one of the most difficult sections that we cover. So I have all the pieces now that I need because I need to do R1 times R2. So Z1 times Z2, which is what I'm trying to do, find the product. I'm going to do radical 2 times 2. So that's 2 radical 2. Then in brackets, I'm going to have cosine of theta 1, which is pi over 4, plus theta 2, which is 11 pi over 6. Then I've got plus I sine, and then theta 1 plus theta 2 again. So pi over 4 plus 11 pi over 6. Now I just need to simplify. It does say to leave it in polar form. So I don't need to simplify everything, but I do need to simplify what's in here. So if I get a common denominator between these two, 4 and 6 would be 12. So this would be 3 pi over 12. This guy over here would be 22 pi over 12. When I multiply both by 2 here and multiplying by 3 here. So that gives me 25 pi over 12. So 2 radical 2 cosine 25 pi over 12. And then obviously it's going to be the same thing over here. So plus I sine 25 pi over 12. And then that is going to be my final answer. It's in polar form. All right, moving on. Example 4, find the quotient of the complex numbers. Leave the answer in polar form. All right, this one is much easier because my originals are already in polar form. So I don't have to do all this background work before I can even use my formula. This is just going to be more of a plug and chug. So here's the formula right up here, quotient of two complex numbers. So I'm doing Z1 divided by Z2. And it says to take R1 divided by R2. So here's R1, here's R2, so 10 over 4. And then on this one, I've got cosine of theta 1 minus theta 2. So theta 1 is 50, theta 2 is 20. So 50 degrees minus 20 degrees. And then it says plus I sine again. And 50 degrees minus 20 degrees. So now I will just reduce and simplify. So 10 over 4 gives me 5/2. And then I have cosine 30 degrees plus I sine 30 degrees. So much easier on that one. Example 5 wants us to use de Moivre's theorem. So we're taking the power of the complex root. It says write the answer in rectangular form. So that means that once we've got our answer in polar form, we do need to simplify it because we want rectangular form for our final answer. So following along here, and really, if you're paying attention to the directions, this section is difficult because it has so many formulas, but because I'm suggesting that you always put these in your box, and certainly you can use the formulas on the quiz, since you don't have to memorize them, if you're paying attention to the directions, a lot of it can be plug and chug. So first what I'm going to do, it says I'm going to take r to the nth power. So the r in this polar form is radical 2. My n is 4. So that means I'm going to take radical 2 to the 4th power. And then it says I'm going to multiply that times the cosine of n times theta. So n is 4. So it's going to be 4. I'm just going to put it over 1 times my theta, which is 5 pi over 6, and then plus I sine, and then it's going to be n theta again. So 4s are not coming out super well today. Sorry about that. 5 pi over 6. Okay, so now I'm going to simplify. Radical 2 times itself is 2. And since I'm doing the 4th power, that means I've got 2 times 2, which gives me 4. So I'm going to have a 4 out in front. And then I'm going to have cosine. When I multiply these together, that's going to reduce to a 2 and a 3. So that's going to give me cosine 10 pi over 3. And then plus I sine 10 pi over 3. Now, if it had asked for the answer in polar form, we would be done. This would be it. But since it wants rectangular, we need to actually evaluate here. So 10 pi over 3, when I look at it as a mixed fraction, that's 3 and 1/3 pi. So when I'm looking at finding that on the unit circle, because it's not, a given unit circle value, it's bigger than a full rotation. So 2 pi would be here, 3 pi lands here, and so then I go another third, which means an additional 60 degrees. So I've got the 60-degree reference angle in quadrant 3 is what I'm looking at. So at 60 degrees, my cosine value is 1/2, and it's negative since we're in quadrant 3, and then negative radical 3 over 2 for the sine value. So that means I've got 4 times cosine, which is negative 1/2, plus I sine of, and then, oops, not sine of, I already did the sine. The sine is negative radical 3 over 2. So then my final step is just to distribute my 4. Sorry about this guy there that I had to scratch out. So 4 times negative 1/2 gives me negative 2 for my A part of the A plus BI. And then for the B part over here, again, I'm going to accept this a couple different ways. The 2 and the 4 are going to reduce, so negative 2I radical 3 is how I would usually write it. I would also accept negative 2 radical 3I. So that is our final answer. It's in our rectangular form that we needed. All right, last one. Complex cube roots of 4. So on this guy, we are looking at, let me scroll to where you can see it, complex roots of a complex number. We're looking at this one, and it wants us to find the complex cube roots. So cube roots, that means that's telling us that n is 3. So everywhere I'm plugging in an n, I'm plugging in 3. Also, I know that because n is 3, that I'm just going to use 0, 1, and 2 because it only goes up to n minus 1, and 3 minus 1 is 2. Now, the problem with this is that the formula is for polar form, and they just gave me 4, which is obviously in rectangular form. So I'm going to need to do some converting first. So we'll do that, and then we'll scroll back up to look at the formula again. So 4 in complex form is 4 plus 0i. So if I am looking for its r value, that would just be the square root of 4 squared plus 0 squared. You don't actually have to write this out. I know that many of you can just look at that and know that that's going to be 4. But just to illustrate it, that's how you would find your radius value. Then I know that the tangent of theta is b over a. So that means I'm doing inverse tangent of 0. And so I know then that I am working with a quadrantal. And quadrantals, in order to have 0 as the value, it has to be 0 in the numerator. So that happens in 2 places. If we look at the, remember, here's all the ordered pairs of my quadrantals that look like this. So if I have this 0 in the numerator, because it's sine divided by cosine, is only going to happen on my x-axis. And because this is a positive 4, I know I'm over here, which means that my value is actually 0. Because we're always looking between 0 and 360. And I don't need to use 360 because it happens at 0. So inverse tangent of 0 on the right side is actually 0. So 0 as my radian value. So now I have my theta and I have my r. So that means now I can use the formula. So I'm going to start, because we are going to start with z sub 0, because when we look at the formula, it's always z sub k for k equals 0, 1, 2. So z sub 0, I'm going to do the cube root of r, and then I'm going to do cosine of theta, which is 0, plus 2 pi k, which is 0, divided by n. So writing this out here. So we have the cube root of r, which r we said is 4. Then I have cosine of theta, which is 0, plus 2 times pi times k, which is 0. That's this guy. This should all be divided by my n, which is 3. And then the I sine part, then I'm just going to repeat this. Now, I wrote the entire thing out so that you can see each time what's changing. Again, I know that many of you look at that and are like, why is she writing that out? I know that that is 0 because I'm multiplying 0 here, and 0 divided by anything is still 0. So yes, that is most definitely true. So I end up in this case with cube root of 4. And then I've got cosine 0 plus I sine 0. And this is polar form. Remember that it's asking for our roots in rectangular form. So that means I do actually have to evaluate in this case. So cosine at 0 is 1. So I've got cube root of 4. And then I've got 1 plus I sine of 0. Sine of 0 is 0. So I times 0 is just 0. So that means that my z sub 0 is just going to be cube root of 4, because it's cube root of 4 times 1. And so that's it for that one. I really, you guys can go on the back, but I can't, so I'm really going to need to squish to fit these all in here. So now I'm going to move on to z sub 1. And so for z sub 1, remember that this is the k value. That 1 is the k value. The n value isn't changing. So I still am going to have the cube root of 4 out in front. The only thing that's changing is the k up here. So now k is 1. So plug that in. So I've got cube root of 4, and then I've got cosine, and now it's still theta up here. So don't change this to a 1. That was theta, not k. So I've got 0 plus 2 times pi times 1, which is 2 pi over 3, plus I sine of the same thing, which since I'm short on space, I'm going to go ahead and simplify. 0 plus 2 pi we know is 2 pi, so 2 pi over 3. So 2 pi over 3 is in quadrant 2 with a 60-degree reference angle. So 60-degree reference angle. And in quadrant 2, if I'm looking at my ASTC over here, the sign is the -1. So at 60 degrees, I know it's going to be the same as what I had written up here, except sine's negative, cosine, or sine is positive and cosine is negative. So it's going to be -1/2 positive radical 3 over 2. So I've got square root of 3/4. And then cosine of 2 pi over 3 is going to be the -1/2. And then the sine, so I've got I times radical 3 over 2. And in this case, because if I distribute this, it's not really going to help me any, you can leave it like that. You don't really need to distribute that because you've got a cube root with a square root, and we're not going to be dealing with the simplification of that. It's unnecessary. So there's my z sub 1. I know I have one more to do because, again, if n is 3, that means I go up to z sub 2. So z sub 2 equals cube root of 4 cosine. My theta is still 0, but this time it's 2 pi times 2 over 3 plus I sine of the same thing. So I can see that this is going to give me 4 pi over 3. So when I go to simplify, 4 pi over 3, that's 1 and 1/3 pi. So that actually is the same value that I had in example 5. So when I go to simplify into rectangular form, I know that the cosine is going to be -1/2, and the sine value is going to be negative radical 3 over 2. Don't forget that I. And then just like in the one before, really the only difference between z sub 1 and z sub 2 is the sign right here, but you can leave it just like this. So we have found the complex cube roots. We have 1, 2, 3 of them, so we know we found them all, and that will wrap it up for us. So again, I strongly suggest that you take a lot of time on this homework, really trying to make sure you understand it. Make sure that you ask your teacher if you have questions.